Alrighty, so what we're going to do is we're going to go all the way back to primary school, so year 6 and year 7 math, and build up our rules around geometry. Ready? Alright, for this we have to just go back a little bit and do some stuff that's probably going to seem really straightforward, but where we're likely going to change a few things is we're going to use explicit names on particular rules that we focus on. Reason for this is we just need to know the language for what comes later in the topic. So we're building up to doing circle geometry. We're starting off doing some angles, triangles, and then parallel line reasoning. So starting off over here, we have 3 different relationships. These are just angle relationships. Now, if you have a look over here, what sort of angle is over here?
Right angle.
It's a right angle. So what we find is that if we have a right angle and we know that 2 angles sum to be a right angle, we call that a complementary relationship. So the conjecture would be alpha plus beta is equal to 90 degrees. And the reasoning for this is it's a complementary. So that's our reason, this is our conjecture. This guy over here, if we have 2 angles and they sum to a 180 degree angle, then what we call that is it's a supplementary relationship. So our conjecture is that alpha plus beta is 180. And the reason we have to think that is it's supplementary, or sup for short. Now, down here it's not really mentioned much in the textbook, but if you have any number of angles and they all sum at a point, then we know that these guys are going to sum to give us 2 pi, or 360 degrees. Now there's 2 things you could write here. It doesn't matter what, there's more things you could write, but you can do one of 2, I guess. You could say it's a revolution. Or alternatively, you can just call it angle at a point. It really doesn't matter what you decide to describe it as. Describe the first 2 as complementary, supplementary, but the third one, it's whatever you really want to call it in a way that makes sense. Okay, so we move along and we're focused on our triangles now. Do you remember your triangles, Foreman?
Kind of.
If all the sides of a triangle are the same, what do we call it?
Equilateral.
Equilateral. So it's an equilateral triangle. Why? Because all the sides are the same. This guy over here, I didn't draw all the symbols on it, but there's a right angle. What would we call that?
A right angle triangle.
Right angled triangle. You can also get acute and obtuse right angled triangles, but I mean, who cares at this stage? It's just a right angled triangle. Now, if all the sides of a triangle are different, we call it a scalene. And if 2 of the sides are the same, this one's really important for spec mathematics. We call it an isosceles triangle, or isosceles if you want to pronounce it correctly. This one's quite important because a lot of the relationships that we identify in the spec math course rely heavily on the isosceles triangle properties. In particular, these guys are all 60 degrees, and these angles here, they're the same. Alpha, alpha. Seem cool? For the scaling, the angles are whatever they want to be, really. They're just different from one another. Now this leads us into the two, I guess, principles. Firstly, I'll get rid of that and we'll just call this gamma. There's two things that we can pull from these. These are actually from the parallel line reasoning topic. If we sum all the internal angles of a triangle, so alpha, alpha plus beta plus gamma, we get 180 degrees. And if we go for the external angle over here, this external angle is going to be, oh, I'll give it a name. This is alpha, this can be delta. Yep. Delta is equal to alpha plus beta. And these two rules are internal angle, angles of triangle, and this one over here is external. The external can be derived just by contemplating that this is a supplementary angle over here. So if it's a supplementary angle, then alpha plus beta are going to give you, gamma is going to be 180 degrees take away alpha plus beta using the first rule. And then delta can be found by just taking 180 degrees take away delta, and it just gives you that. So it's pretty elegant, really. So those are the rules around triangles. Now, the triangle rule, the first one, the internal angle sum, it actually comes from our parallel line reasoning. In fact, a lot of our math comes from this idea over here. Now, when I was first looking at these, when I was learning, I'm like, man, how does anyone remember any of these? But there's one simple perspective you can look at it to make everything make perfect sense. And you don't really have to remember them off by heart, you just know them. Imagine that we have two lines, and these lines point in the same direction. Now, if these were vectors, how would they differ from one another? They have the same direction, but what's different about these two lines? Same direction, but different place. Yeah, they're translated. So it's the exact same line, but it's in a different position in space. Now, suppose that we cut the lines with a transversal. So the line that's cutting these two parallel lines, we call it a transversal. If we cut the same line with the same angle, being a different place, is there going to be a different interaction between the two lines, or are they just interacting the same but in different location?
Oh, they're not interacting at all.
Really? This line and this line? You don't reckon?
No, I don't reckon.
What do you reckon's happening then? Okay, let's put it this way. If we were in a different classroom but we were doing the same topic, would we be having the same conversation? Probably. Probably. And because of that, if you have the same line but in a different location, its interaction with the transversal is exactly the same. It just happens in a different location. So if we look at this, if we're interacting with this line over here, we'll start off down here actually, this angle. So think about, we have a parallel line that's being cut, and this angle over here. Now if we cut the same line but in a different location, and this angle up here, are these angles going to be different? Same lines, same cutting angle, different location. Will the interaction be any different? No. And because of this, we have alpha over here and alpha over here. what we discover is that this interaction here, this is going to be called a corresponding. So it's a corresponding angle relationship there. Does that make sense? Now, the other one that we need to look at is we've got these two angles here. Now, if we've got angle alpha and angle beta, what relationship are alpha and beta in?
Supplementary.
They're in a supplementary relationship. Now, a supplementary relationship described across two parallel lines has its own name. We call it cointerior. So the cointerior relationship, if this is beta, we'll call this gamma. It's going to be it will be alpha plus, gamma plus beta is 180 degrees. And this is cointerior. And I'll change this name over here. We'll call it delta. It's about delta. Welcome, Ron. Let me just have a walk behind. So it will be alpha equals delta. Seem okay for now? So it's still conjecture, then reasoning. All right, now up here we have two more. First one that we're going to look at is going to be, let's say, these two here. See how that both these lines are the same, different location, they're cut with the same, but have a look, you've got supplementary across two parallel lines. This guy over here, it's called the alternate. So if this is alpha and this is beta, then our alpha plus beta is going to give us 180 degrees. Can you see it? Supplementary across two parallel lines. And then there's one more. I'm going to draw it differently. These two over here, we'll call this gamma and we'll call this delta. Gamma is equal to delta. And this one's technically not a parallel reasoning, but we're throwing it in anyway. We call it vertically opposite, and we can extend this even further. In a way, it's a bit of a corresponding angle, but what's your favorite Greek letter after delta?
I haven't studied them in a while.
Epsilon. So let's say epsilon as well. Technically, it would be a corresponding to delta, but if you see them like that, you can also argue it's vertically opposite. Does that make sense? Now, in terms of what this would look like at a stage 2 level, we don't state the rules. We don't need to state the rules, but at a stage 1 level, to demonstrate that we understand the rules that we're using, we have to know all the names of the rules and we have to know the relationships they have to one another. Does that make sense?
Yep.
Are you happy with that so far?
Yep.
Do you remember all of it? No, that's why we practice. All right, so what we'll do is we'll have a go at a practice question. All right. Find the unknowns. Two parallel lines were zooming through space and they were cut by the transversal. The angle over here, what did we say this was?
-8 to -11,
I got -8.
What angle size do you reckon it is?
Alpha?
I'll just put
80,
yeah, that's what I did. Well, did you
7.
have that?
67 degrees. And then this over here, this was A, this was B, this was C. Now, using our parallel line reasoning or otherwise, find all of the unknowns. Okay, what do you know?
I know 67 degrees.
67 degrees. How does 67 degrees relate to B over here?
It is
What's their relationship? I erased it.
supplementary.
It's supplementary. So because of that, supplementary angles sum to give what?
180.
180. So 100 and, actually no, we'll write it as B plus 67 degrees gives us 180. Why do we think that? Because it's supplementary. Sup. Therefore, B is what?
180 minus 67.
Which is? $103. Simple.
113. Isn't it 113?
113.
113. Not cool. Alright, next one. What angle could we solve here?
Solve for C.
Solve for C. What's the relationship between this angle and this angle? Or it could be this angle and this angle. You know what B is, so we're allowed to use it if we want. How can we relate B to C?
Their corresponding angle.
Their corresponding angles. If they're corresponding angles, what's C going to be?
113.
C equals B. C equals 113. Why? Well, they're corresponding. Cool? Next one. What else could we learn?
We could learn A.
We could learn A. How does A relate to any of these known angles here?
We can relate A to C.
We could relate it to C, and that would be what relationship?
Supplementary.
It's supplementary. So done. How else could you do it without using supplementary? Is it corresponding?
Vertically opposite.
Could be vertically opposite. So A is equal to 67, is it? Through what reasoning?
They're vertically opposite.
Because they're vertically opposite.
What do you say?
Just abbreviate. And then D, Wunderschirm.
Do we get two double-sided A4 cheat sheets for spec and methods?
Not sure about methods.
D is identical to C,
D is identical to C. What relationship is that? Starts with C.
corresponding.
Corresponding. Okay, D is equal to C. Why they're corresponding. Booyah. So basically all you're doing in this topic is you build up a repertoire of known rules and then you make a conjecture and then you justify your conjecture based on a rule. We do this until we get about 10 rules deep, in which case we can solve a lot of circle geometry questions using these, which don't necessarily, you'll never get a question like that in stage 2, but you might solve a question using this geometry or your knowledge of geometry, or you'll simplify a question so it becomes basically routine, or not even routine, trivial, by using these known rules. Seem okay?
Yeah.